So welcome. So this is our second video in this series, and we're going to talk about dimensional analysis. And if you're anything like me, you think that dimensional analysis is like totally boring and book work and busy work and all that. And then as I went on in science, I found out that it's actually kind of fascinating. There is a little bit of a boring element to it, but there's also a really interesting element to it, which is kind of nice. So dimensions. Dimensions are the things that we attach units to. So we measure length in meters, so the unit is meters, but there's a dimension called length. There's a dimension called mass. We measure it in kilograms. There's a basic dimension called time, and we measure it in seconds. We cannot add things that are of different dimensions and get anything that makes any sense. If we turn around and say, 7 kilometers plus 5 kilograms equals 12 somethings, it's like you just added, 5 thoughts plus 7 carrots. I mean, it's like it's pointless. You can't add things that are different dimensions. You can't subtract things that are different dimensions. They've got to be the same thing. But you can multiply and divide things that are different dimensions. So we talk, for instance, about speed being, it's a length divided by time. So the units are meters per second in our system, but it's fundamentally a length divided by a time. Okay, so whether we have complicated dimensions or simple dimensions, for example, we can add velocities to velocities, so we can add meters per second to meters per seconds. The other thing is, on an equal sign, on the left-hand side of an equal sign and the right-hand side of an equal sign, we have to have the same dimensions. Because not only is the left-hand side numerically equal to the right-hand side, the left-hand side is dimensionally equal to the right-hand side. So we have 3 basic dimensions, and we can only add and subtract in those dimensions if they're the same, and we can only have an equal sign if they're the same. So that tells us a lot about equations. So I'll give you an example. If I say, I lost my pen, I'm sorry. I do that occasionally. There we go. If I say VF equals VI plus AT. I know that's wrong. So plus AT squared. I know that's wrong. And the reason I know it's wrong is because the dimensions are not the same. If you think about it, my velocity, that's meters per second, so that's length over time. And to make sure we don't get confused, we put our dimensions in little brackets. So it's a symbol that has 3 parts. It's not big T in a bracket, it's dimension T. So there's my velocity, and then my V initial is my velocity. So there's no problem there. But then I come to this plus A. A is acceleration, which is meters per second squared. So that's going to be length over time squared. And then I have time squared. Oh man, that's time squared. Can you see what I did there? Can you see how those two cancel? And so I have meters, length over time equals length over time plus length. That cannot be. So if you're kind of saying, is that square there or not? If you look at dimensions, just get rid of that square, and that means that guy cancels with one of those, and I get length over time and length over time. So dimensions can be your best friend as far as figuring out, does this equation even make sense? If you're trying to remember something, it's your choice between 2. One of them will make sense. The other one will not make sense. It won't help you with numerical coefficients. It won't help you with, is there a half there, or is there 2/3 there? Is it 0.76 times something? It won't help you with that, but it'll help you with the actual parameters. So dimensional analysis cannot tell you about coefficients, but it can tell you about the parameters that should be there, and so we see. okay, so we're going to do a little bit of, that kind of stuff, which is it's going to be okay. But here's the fascinating stuff. And that is, that same way of thinking really informs you about the physical world. Here's the story. So back in the 1940s, 1945, the US dropped the 2 atomic weapons. It changed everything. Even the scientists who worked on it, half of them were horrified. It was far more destructive than people. You can say it's a 100,000 TNT tons. You can say it, but when you see what it does, it's like, oh my word, we can destroy the earth. For the first time, science, not nature, could destroy life on a massive scale. And society reacted. Society turned around and said, who exactly are these people who are making these things? Especially because, and I didn't know this until quite recently, especially because the president who dropped the bomb was a new president. The old president just died, so he took over just before the decision was made. And it's not clear that the president actually made the decision. It was an army project, and the army were running it, and they dropped one bomb, and then there was no response, so they dropped a second bomb, and there was, well, we'll drop a third bomb then. As soon as they could make them, they were going to drop them until they got, the outcome that they wanted. So it wasn't even like the president was like taking these decisions. It was this military machine that was kind of running itself. And at some point, the president said, enough, you will not drop a third bomb, we're going to... But the society, not just in America, but all over the world, started saying, who are these people? And it was this first idea about scientists as being kind of scary, very scary individuals. And a couple of things happened. One was, I don't quite understand how this works, but you started getting a lot of horror movies about wacky scientists really messing things up. And you started getting the emergence of the Mr. Spock, Star Trek's Mr. Spock, all logic, the cool, calm scientist. Wears a lab coat, wears glasses, a whole bunch of pens, has a clipboard, unemotional. That's what a scientist is like. Scientists are not like that. Scientists are egotistical, they're bratish, some of them are wise, some of them are rash, some of them are highly competitive, some are not competitive. They're just like everybody else. And so this idea about scientists as being rational and unemotional was kind of promoted, and when it was promoted, was encouraged, certainly by the movers and shakers in society, because in a way it means that scientists' ego is taken out of it, so we're not so scared of them. It's like they just do the science, and then our elected politicians decide what to do with it. So don't worry. It's basically, don't worry. Everything's going to be okay. Well, that's true. That's not true. Scientists, just like everybody else, although there is this cultural thing now about science should be big science should be in the hands of government and should be controlled. Unfortunately, there's this tendency where a lot of people are scared of science. The solar eclipse. My daughter's old school was not letting the kids out to look at it, banning them from going out to looking at it. And the science teacher's going, I teach about this. You can't not let them go out. There are safe ways to view. And they had this idea that somehow the sunlight in an eclipse was different from the sunlight normally, and so they were going to get irradiated with... And it's a little bit of caution that's been, because people have never done it, because they don't know, gets really changed. There's this deep-rooted fear of science in a lot of people. It's like they don't know about it, and they don't really want to know about it, because science can bite you. On the other hand, there's a feeling in science of, we're the ones, we know what we're talking about, and all these other people are idiots. And why should I explain this to you? There's a classic case when 3 Mile Island happened, and they'd had a partial meltdown of the core, and there was radioactive gas in the dome, and there was worries about it escaping, etc., explosion, etc. And so the whole of the country is looking at Harrisburg, Pennsylvania, and Jimmy Carter, who was the president, who was a nuclear engineer in the Navy, as president, had flown down and kind of like, look, the president's here, it can't be that bad and all that kind of stuff. And they're trying to manage the situation. And it's not run by the government, it's run by Westinghouse, I think it was Westinghouse, a private company. And the lieutenant governor, the elected, one of the elected officials for Washington, for the Pennsylvania, is kind of calming things down, and he's saying, this is okay, it's all contained, like that. And there's been no leaks, nothing's happened, everything's great. So one thing is, years later he finds out that the engineers who were working for the company had lied to him, knowingly lied to him. There had been an escape, but they didn't want to say it. So he was saying things with his hand on his heart, believing them to be true, and they weren't true. That was one thing that happened. And the other thing that happened was there was a press conference, and the lieutenant governor stops talking, and then some of the engineers are brought on, and a newspaper, a journalist, asks a question, and the response of the engineer is, well, I could answer the question, but there's no point because you wouldn't understand my answer. Can you imagine saying that? It's like you're talking to the mouthpiece of the people, and you're saying, oh, you're just too dumb to understand this thing. It's like, so one of the reasons, I look at nuclear energy. Nuclear energy is beautiful, but when it goes bad, it really goes bad. So I got some caution about it. But man, if you have that attitude about we know and you don't, then do you want those people in charge of nuclear power plants? And I think that's partly what happens with this kind of stuff. When people who know about it kind of get a bit arrogant about knowing about it, it's just bad all round. And so a lot of people are very concerned about nuclear power, and I think I am too. Because it's kind of like that little exchange tells a whole lot about the way that things can work. So as engineers, I think physicists also have tremendous egos, actually. Our friends and neighbors might not know this stuff, and we might not know how to do poetry, So we got to educate them a bit, and they got to educate us a bit. And it's a shame in the technological society more people don't know more about science. But we're not going to encourage that by just forming a club and excluding everybody else. So, with case in point, when all the science fiction movies came out in the 50s about, scientist does some radioactive thing and causes a mutation and makes a spider the size of a house, and it's terrifying the neighbors. You can find all these things on Netflix. The old videos are there. There's a whole bunch of this genre of video. The scientist does something crazy, usually with radiation, causes some natural disaster, and there's some monster stalking the neighborhood. And it's really striking a chord. The reason why it's effective is because it is striking a chord in people's hearts. An awful lot of the physicists and engineers are at the back laughing because it's physically nonsense. And this is why that's physically nonsense. We talked about the difference between prefixes in one dimension and prefixes in 2 dimensions and prefixes in 3 dimensions. So we want to talk a little bit about some dimensional analysis on this. So let's take a potato or a spider or whatever. I'm going to represent whatever it is as a cube. Doesn't matter. The shape can be as complicated as you like, as long as the shape does not change. And I'm going to make that shape twice as big. So first problem is, what do I mean by that? What I mean by when I say twice as big is not twice the mass. It's not twice the volume. Twice as big means twice as tall and twice as wide and twice as deep. Its linear dimensions are doubled. So I'm going to, my linear, I'm going to do times 2. Now I can visualize that. It's like that now.
and it must be like that. So that's the width done, and then it's like that. So I've got this like wall. Oh man, but there's also, if it's a cube, it's twice as deep. So there's that. So can you see I have a front wall there, I have a side wall there, and I have a top wall like that. Can you see that reasonably well? Now if you think about it, that front surface, there's the area of one thing. How many areas are there now in this thing? There's 4, isn't there? 1, 2, 3, 4. So the area is times 4. Let's look at the volume. So there's a cube. There's the original cube. How many cubes do I have now? 8. So there's this dimensional relationship. If you double the linear length, you got on any area, no matter what its shape is, as long as you keep the same shape. If you double the linear length, you have 4 times the area, and you have 8 times the volume. That's the way it works. If you do the same in all dimensions, double, triple, quadruple, whatever, that's the way it works. If I triple my linear length, now I have times 9, 3 times 3, and times 27. Now, I jumped a step there, didn't I? The way I got that 4 was really, I had times 2, and then I had times 2 squared, and then I had times 2 cubed. That's how I got the 4 and the 8, yeah? I visualized it, but mathematically that's how I get it. For the cubed, I have times 3, I have times 3 squared because it's an area, and times 3 cubed because it's a volume. So that would be 3, 9, and 27. Let's do times 4. That would be times 4 squared, and times 4 cubed. Well, 4 4s are 16, and 4 16s are 64. Okay? So 5 would be times 5 times 25 times 125, and so on. Yeah. Times a half would be times a half times a quarter times 1/8. Yeah. So it goes on like that. Good. So this is interesting. It's mathematically rigorous. That's the way it's got to work. You take a spider, you make it 100 times bigger, then it has 100 times 100 the surface area, and it has 100 times 100 times 100 the volume. Now we ask ourselves some physical things. Your muscles. What counts about your muscles is it the volume of your muscle that determines your strength, or is it the cross-sectional area of your muscles that determines your physical strength? Anybody got an idea? When you see somebody with muscles, it's cross-section, isn't it? It's like strands. Muscles are like strands of fibre, and the stronger you are, the more strands of fibre there are. So the more pieces of string you've got pulling your arm up. So your strength goes with area. But your weight, what does your weight go with? Does it go with your linear dimension, or does it go with your area, or does it go with your volume? Volume. Can you see the problem here? If I make this spider 100 times bigger, 100 times taller, 100 times wider, 100 times deeper, I've made it 10,000 times, 10 to the 4. I've made it 10 to the 4 times stronger. But I've made it 1,000,000 times heavier. So it's stronger, but it's much heavier. And what happens is you get to the stage where it doesn't have the weight, it doesn't have the strength to hold itself up. So when people see this, when the scientists and engineers see this, they laugh because they know a spider that's as big as a house would lie on the floor panting, unable to lift its legs or do anything. It completely cannot work. That's important. You want to build a model to see how a boat behaves in different weight conditions. You're making the boat much smaller. So dimensionally, it's going to be really messed up. Its surface area is not going to be right, and its volume is not going to be right. So it's not going to behave the right way. So the model you make doesn't actually look that much like the boat. Dimensionally, it's like the boat. It's a ratio of dimensions. It's not It won't look like an Airfix, one of those plastic models you buy at Michael's. It's going to look different because they've got to change that to keep the proper ratios the way they are. And this also, so anybody love biology here? Okay, if you did biology, do you remember being taught about the cell? How amazing the cell is. It's got DNA in it, it's got RNA in it, it's got some other stuff in it. I never did any biology in my life. It's a shame of the British system. I did physics for 5 years, bit of chemistry, nothing else. Okay, there's this cell, and we can have a single-celled organism called an amoeba. Amoeba. And I remember my buddy at the high school was a biology teacher, kept going on about the wonder of the single-cell organism and how great it was. And I said, well, if single-cell organisms are so good, why don't we have a single-cell organism the size of, the sun dome? I mean, they're great, just have them rolling around the place. Why do we only have little ones? And he didn't really have a good answer, and neither did I, actually. But here's the problem. So here's a single-cell organism. It's small. And it gets bigger and bigger and bigger. It starts being unhappy. And the reason why it's unhappy is because when it was small, it needs food, yeah? How does it get food? It absorbs the food through its skin. So if I double the size of the amoeba, its surface area is now 4 times bigger, but its weight, which is its hunger, because weight goes with hunger, or hunger goes weight, is 8 times bigger. So if I double the size of my amoeba, I have, let's do it here, I have 4 times the surface area, so I have 4 times the ability to eat, but I have 8 times the hunger. If I make it 4 times, I have 16 times the ability to eat, but I have 64 times the hunger. Make it 10 times bigger. I have 100 times the ability to eat, but 10,000 times the hunger. And so it's problematic, yeah? You starve. So what the amoeba does is say, man, I need more surface area. So it divides into 2. Same volume now, but double the surface area. Well, not double the surface, but more surface area. So it's a way of keeping track. And then in industrial, it turns out most of our food, if you go to a restaurant, it's all industrialized. I mean, I'm not a Luddite. It's not that I'm against industrialization, but you don't realize, you have this idea that somehow that food was somehow carried from a field, and you don't realize that it's been processed quite a bit, actually, especially in a restaurant, and especially in a fast food restaurant, because fast food restaurants are highly technical places. Industrial engineering. That's industrial engineering. And so I came to the States in 1979 for a visit, and the thing that really struck me was the fast food was nothing like that in Britain. And just the uniforms and, the whole thing. It wasn't quite like it is today. You had people at podiums with microphones, and you'd say, I want burgers, and they'd say burgers, and somebody would get burgers. Fries, somebody would get fries, and all that kind of stuff. So I had this experience. I was quite taken by it. I went back home to England at the end of that trip, and I was with my mom. We were in I was working in Manchester, and we're in Manchester, and we went to a fast food restaurant, and I said, let's eat there, Mom. And she goes, okay. And she said, I don't know what to order. And I said, just follow me, Mom. So I said, burger. So the guy goes, burger. And I go, fries, Coke, and Coke. So my mom steps forward. And she goes, burger. And she goes, fries. And then she goes, I'd like a medium-sized hot tea with just a bit of milk and a bit of sugar. So the guy goes, hot tea, milk, sugar, like that, And then he takes our money, and then he goes, it'll be about 15 minutes. So they'd got all the uniforms down, they'd got all the display of it, but they didn't have the fast food. Because we're still making English food. Because English food consists of potatoes, chips. They call them fries, but they were chips. They were big, meaty potatoes. And you can't make what we would call them, home fries, I guess. Yeah. You can't make those quickly. Here's what's going on. If I make this potato twice as big, it's got 8 times the volume, which means it needs 8 times the energy to cook it. And the energy comes through the skin. And so it only has 4 times the surface area to get the energy in. So it takes twice as long to cook. You need 8 times the energy, but you've only got 4 times the surface area. So you've got to wait twice as long for the thing to cook. And if you make it even more so, it goes dimensionally, it falls off. So the reason why you have skinny fries in fast food restaurants is because you can cook them up so quickly. So they also taste really good, but that is using dimensional analysis to fundamentally design an industrialized food process. And just other things. My wife, about 10 years ago, 15 years ago, said, I'm not cooking anymore. And I said, fair enough. And I'd been a single guy for 45 years. I was used to cooking. I was fine, no problem. And I understand. She was like, we had a daughter, and you know, she was by necessity doing an awful lot of things with our daughter, and she was just so tired. So I thought, this is fine, I'll do it. So I said, it's not going to be very good food. You know, it's going to be my cooking. She goes, I don't mind. So I started cooking, and it was, oh man, I'd had like a few years of her cooking, and my cooking was like so bad. And it was like, so I thought, I can get better. So I started trying to pay attention to it. And one of the things I realized was half my food was overcooked and the other half was undercooked. And it was because I wasn't doing simple things like you get potatoes, you don't put a big potato in with a little potato and boil them. Because the little potato will cook much quicker than the big potato because the surface area to volume ratio is not the same. So you cut your potatoes up to make them all the same size. And so then when you cook them, when one's ready, pretty much they're all ready. You see that? That's dimensional analysis affecting how we do things. Most people do it because they don't even think about it. They just like, you know, intuitively they know to do it. For some reason I didn't intuitively know to do it. So dimensional analysis can seem a bit boring, but it's actually really, really insightful in the end. Let's do an example of this. This is a question. So in a test, I wouldn't say, show that the dimensions of S are. I would say, what are the dimensions of S, given that S is equal to 5v squared over m. And I tell you that v stands for velocity and m stands for mass. So the first thing to realize is 5 is dimensionless. It's a complete red herring. It's nothing to do with your dimensions. So you ignore the 5. And then the way I do them is I turn around and say, well, my velocity would be meters per second, and that's squared, and that is kilograms, okay? And then I say, okay, let's put this in dimensions now. So I have length over time, and that's all squared over mass. I've got to be in dimensions in the end. Let's get rid of this square first of all. So that's length squared over time squared. You've got to square top and bottom. Sometimes people make that mistake and they forget about that. And then we have mass. And now we've got to have things in just 2 levels. You can't have a triple decker or a quadruple decker thing. So I put my length on the top, squared, and we put our that on the bottom. And then I've got to decide what to do about this mass. And really that's m over 1. And we flip it, yeah? Yeah. So it becomes 1 over m. And sometimes people will put the m on top and sometimes it should be on the bottom. If you're dividing by a fraction, you flip it. But when there's not a fraction there, it just makes the number small. So you might say, will this make my answer smaller or bigger? And if it's bigger, put it on top. If it's smaller, keep it on the bottom. So then there's my dimensional analysis. There's my dimensions. And there's my answer. So that's what I'm looking for on this. I don't mind you using units to get going, but I can't accept units as the answer. And you need to be using the symbols. You need to be doing it right. It's capital. It's not little m, it's big M. It's not little t, it's big T. It's not little l, it's big L. They're stamps. They're like little tattoo stamps or something. Can you do the one on the bottom? If I set a clock, can you ever go at that? Oh, I didn't stop that one. Let's start this. So can you ever go at that? It's B equals V over 2m squared, where V is velocity and m is mass. Hopefully the right answer's there. It's going to be... Yeah. And plug it in as you get the answer. If you're not going to do it, I know some people they just stare at me. Just put anything in. Put an E in if you like, so that I'm not waiting for you. I'm sorry, I should have paused that. So. Zoom. Sorry, I just forgot that. So here we are, and I've got to put my video back on. So here's the answer for it, and just check it over. Okay. So for this next bit, there's this classic thing about you run 22 meters in 7 seconds. So you say, I wonder what my speed is, and you find that your speed is 3.12857,143. And if I had a more expensive calculator, it would go on and on forever. So I have a really poor precision measurement of length, 22 meters, not 22.1 or 22.5 or 22.175, just 22. Not 23, not 21, it's 22. That's not a very good measure of length. And I've got a lousy measure of time. I mean, not 5.7 seconds or 5.7275 seconds, not 6. Not 7, not 6, it's just 7 seconds. Lousy length, lousy time, gets me this really precise value for speed. It clearly makes no sense from a science point of view. Mathematically, yeah, it's true, but from a science point of view, it's called dividing your way to precision. Lousy length measurement divided by a lousy time measurement gets you a really precise speed measurement, and it cannot happen. And so we have to be careful about how we write numbers down in our measurements, and we have to be careful about how we write our numbers down in our answers. And we keep track of that, and we keep track of that using significant digits is one of the ways of doing it. So we divide the world up into qualitative and quantitative, and qualitative has some value. It's hot, rather than cold, it's got some value. But we tend to like numbers. I think it was Lord Rumford, a thermal guy, said you don't really know about something until you can put numbers to it. You don't really understand the science until you can put numbers to it. So we prefer numbers. And there's two types of numerical values. There's counting how many cars are in that parking lot. There's not 572.3 or 0.4, there's 572 or there's 573 and there's none in between, you know. So that's a counted value. We say that's exact. Sorry. And we say that's exact. And then we have what we call measured, and the measured value is how far is it to that lamppost? And the answer is it depends on what you give me to measure with, to be honest. If you give me a really crude measuring tape, I'll get you a really crude answer. If you get me a laser-guided interferometer, I'll give you it's within a few angstroms. It's like, I'm going to write down the numbers completely differently. So we have exact measurements and we have measured measurements. And the trick is, whatever we write down for a measurement, we should be able to visually read all the digits apart from the last one. The last one is a guesstimation of a partial bit. So if I have a millimeter ruler, I can read the number of millimeters. I might express it as meters, centimeters, and millimeters, but I can simply count along the ruler how many have I passed. None of us should disagree about that. But in that last millimeter, we can disagree about, is it 0.3 of a millimeter, or is it 0.5 of a millimeter, is it 0.7 of a millimeter? What is it? And it's acceptable for us all to put down our own version of what it is. When I was younger, I could see probably 0.2 millimeters. I can't see 0.2 millimeters anymore now. So I tend to go 0.5 or nothing. It's like I divide millimeters into two. You can't do quarters. That might sound crazy. Surely if you can do a half, you can just squint a bit and see a quarter. But a quarter is 0.25. Now you've got two digits. You could do 0.3 or you could do 0.2, but you can't say 0.25 because that's two uncertain digits and you're only allowed one. Okay. So what we do is we use a measuring rule. It's something we have to practice. We practice it in lab. We use a measuring system and we've got to learn how to write things down. If I had a ruler that had no millimeter markings but only had the centimeter markings, same measurement, using a different ruler, I couldn't have that decimal place. I'd be estimating the millimeter. And if I had something that was divided into decimeters, I'd be estimating the centimeter. And if I had something that was only divided into meters, I'd be estimating the centimeter. So whatever your ruler has as its smallest value, you can go one decimal place more with a guesstimation. If you're using a mass balance, you go one decimal more with a guesstimation. It's a bit hard with a digital meter. It's like there's it's kind of like what I'm guessing about nothing. We'll get to that in a bit. But what I want you to know is, when you write down a number, we assume that the last digit is uncertain. We're not sure about it, and we're allowed one uncertain digit. The earlier digits are all certain. We should all count the same number of millimeters that we pass when we're getting to our mark point. The earlier digits are the result of observation. Reasonable people may disagree about the last digit, and that's okay. But they should not disagree about the early digits. And we refer to the number of digits in our measure, so we can talk about this thing. We call it the number of significant digits, or the number of, well, sometimes it's called the number of significant figures, but it's really the number of significant digits. We need to be able to state how many significant digits are in a number. So now, I have a whole bunch of measurements here. This measurement was taken with a massing machine, which was not with a ruler, which was not in meters, but in centimeters. And I know that because the next digit is the millimeter. That's in meters, there's my millimeters. My uncertain digit is the millimeter. So it's not a millimeter ruler, it's a centimeter ruler. Does that make sense? Does that make sense? On this one, there's my meters, and there's my, these are called centimeters. Sorry, oh, I'm sorry. Meters, decimeters. No. Yes. Meters, decimeters, centimeters. Okay? So this ruler was in decimeters. That centimeter is uncertain, so the ruler must have been marked in decimeters. In this one, this is meters, decimeters. I'm guesstimating my decimeters. The ruler simply had meters marked on it. In this one, man, I wrote it down this way. It turns out that my ruler was not, well, there's no decimal not in meters, in tens of meters. My rule was in tens of meters, because that's my uncertain digit, and so on. So we can tell from the way a number's written down what ruler or what mass scale we used. The next thing we've got to do is be able to say how many significant digits we have. The rules are different. If you have a decimal point, you've been careful. If you don't have a decimal point, you've not been so careful. I know it sounds weird, but that's the way I think about it. Decimal point. In every case, the left-handmost non-zero digit, is always the most significant. If there's a decimal place, it's rule number 3, the right-handmost digit, no matter what, even if it's a 0, is the least significant. You count all the digits in between them. So this is the most, that's the least. 1, 2, 3, 4, 5, 6. 6 significant digits. Yeah? Most, least, 6 in all. If there's not a decimal place, the right-handmost non-zero digit counts. So most, least, 2 decimal places. Only 2. Those 2 zeros, they're called placeholders. If there's a decimal point, most, there is a decimal point, least, 5 decimal places. So that's 6 decimal places, 5 decimal places, only 2 decimal places, because there's no decimal point there. Could you ever go at doing that next one for me? Oh, there's no answers, there's no choices. So let's just talk through it together. So let's have a look. Looking at things, I think there's my most significant, and there is a decimal place, so that's my least. So how many decimal places do I have? This is 5, isn't it? This was 6, and this was 5, and this was 2. And then here, well, there's my most, and there is a decimal place, so there's my least. So that's 3. Yeah? Forget about the 10 to the minus stuff. There's my most, there is a decimal place, there's my least, there's my most, there's my least, there's my least. 4 significant digits. Forget about the 10 to the e to the somethings. There's my most, there's my least, it's still 4. There's my most, there's my least, it's 2. It's 3. It's 3. Cool. So you need to be, that's something that'll come up. All right, that's how we write down our measured values. What about our answers? Well, it depends if we're multiplying and dividing or subtracting and adding. If you're multiplying and dividing, you look at your 2 numbers and you work out how many significant figures they have, significant digits. That's got 3, that's got 2. Your answer can have no more significant digits than the least of your original numbers. So I gotta work this out. So that should be 26. So that should be 26. Sorry, 26. So let's go through this. So you can just do it that way. I can prove it to you, especially as I put down the wrong answer. I can prove it to you by doing a long division, a long multiplication. 2 3s are 6, 2 2s are 4, 2 1s are 2, 1 3 is 3, 1 2 is 2, 1 1 is 1. Let's change colour pen so you can see this bit of working in a different colour. Let's do blue. Well, that's an uncertain 3, isn't it? And that's an uncertain 1. So a certain 2 multiplied by an uncertain 3 is an uncertain 6. But a certain 2 times a certain 2 is certainly a 4, and a certain 2 times a 1 is certainly a 2. But now with this 1, it's an uncertain 1, so that must be an uncertain 3. It's an uncertain 1, so that must be an uncertain 2. It's an uncertain 1, so that must be an uncertain 1. So now I add up my numbers, 3, 8, 5, 2, and now I say, oh, I'm only allowed one figure of uncertainty. Well, there's my figure of uncertainty. It's that column that's uncertain. I round my 8 to a 6, and there's my answer. Because that's an uncertain 3, that's an uncertain 8, that's an uncertain 5, and I'm only allowed one uncertain digit. So that's the logic behind it. What you realize is that, oh yeah, my answer always has the same number of significant digits as the worst of my original measurements. That's the logic, but that's how you remember it. If we do addition and subtraction, then it's a slightly different situation. Let's do 1, 2, 3 added to 5.35. So I get 5, 3, 8, 2, 1. Let's change coloured pens again so you can see the difference. No, sorry. So that's an uncertain 3 and that's an uncertain 5. So that's an uncertain 5, that's an uncertain 8. I'm only allowed one uncertain digit. So this becomes 1, 2, 8. There's no rounding up because 3 is a small number. And if I look at this, I suppose, oh yeah, they've both got the same number of significant digits, but what's counting here is that this has the least number of decimal places. It's got no decimal places, so I'm not allowed any decimal place in this. Okay? So 2 separate rules. And just got to know them and use them. It tends to be more important in lab than it is in this class. I will ask you a question on significant digits in I'll ask you a question on significant digits in the first exam, and then from then on, when I don't want to keep giving you numbers that are complicated, so there'll be times when I'll say 5 kilograms multiplied by 7 meters per second squared, and you take the 7 and 5 and you get 35 and you'll put 35 down. You're not going to put down 40 because you rounded. You're going to put 35 down. So I talk out of 2 sides of my mouth. Significant digits, I need you to know how to do them, but we're going to ignore them for our calculations because it just makes life easier. I think I told you I used to be on the board that does the teacher training exam for physics teachers, and there were 2 things that caused arguments. One was significant figures, and the other one was the scientific method. It was like everybody's got their own version of those 2 things. So some people insist on significant figures for the rest of your life, and others say it's just a calculation, just run the decimal places, it's fine. And other people on scientific method, they have their own way of defining things, and so those are the 2 things that cause arguments. I'm going to try and get this last bit in before the tape runs out. Conversion of units. This was taught to me by my chemistry buddy, Mr. Fan, at King High School. And basically, it's a layout issue. We all know we use conversion factors. And there's 12 inches in a foot, but do I multiply by the 12 or do I divide by the 12? It depends on which way around the problem is. And people get them backwards. So this is a way you can do this. I've made up some units here. I have 3 pecks per dross. That's 3 peck, 1 dross. That's what that means. 3 pecks per dross. And I want to turn it into meters per second. Well, I tell you that 1 meter equals 6 pecks. So I say, I don't want to have pecks in my answer. I want to get rid of the pecks. Pecks is on top. You put peck on the bottom. That means that the meters have to go on top. Because I've got to do the ratio one way around. 1 goes on the bottom, 1 goes on the top. If I've got pecks on top, peck goes on the bottom for my conversion factor. If pecks were on the bottom, pecks would go on top for my conversion factor. And I just read what I say. I go 1 meter equals 6 peck. And then I go cross, 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 and that's done. And then I say, but I don't want dross. I want seconds. Well, dross is on the bottom, so put dross on top and seconds underneath, because that's the only place for it to go. and I read what it says. It goes 1 dross equals 5 seconds. Dross, dross, dross goes away. Dross, dross, dross goes away. I have 3 times 1 times 1 is 3. 1 times 6 times 5 is 30. So this equals 0.1 meters per second. So that's the factor label method. It works really nicely. It's a layout issue. It's not that people can't do the math. They can do the math. They just, when they're doing it in their head, they will get the conversion factors upside down sometimes. And so they have problems with that. Yes, it's fair game to me for me to expect you to know that there are 100 centimeters in the meter and and 1,000 millimeters in a meter and that kind of stuff. But beyond that, I'll tell you the conversion factors. Okay. Final little bit. Word problems. I really mean this. You can do problems and you can limp your way through them and it will not be efficient and you'll make more slips, even if you know the physics reasonably well. You need a way where you can just answer questions steadily. And they're not all unique. They all kind of follow the same pattern. People over-focus on the numbers. So they'll sometimes give me a square with numbers in it. No equation. It's hard for me to grade that. I can look at the answer, which should be in a box. If the answer's right, whoop-de-doo, the answer's right. If the answer's wrong, I don't even know what equation you're using. So, really look at this, and it's not busy work. Just, I mean this from the heart. You got to form a picture of the physical situation in your mind. You got to do that. It's just if you're not visualizing, if you're trying to do this as a math equation type class, it's not going to work. You'll do the right math on the wrong problem. So you got to visualize. If you can't draw a diagram of it, then there's a big problem there. So the first job is to visualize. And you don't need to be an artist, but you need to be able to draw a diagram. I am a visual thinker. You know, I write these problems with pictures in my mind. If you don't have that picture in your mind, it's not going to go so well. You need to list every parameter. In truth, when you get really practiced, you'll sometimes not list parameters. But at the beginning, you should always list parameters, especially because the problems at the beginning tend to have a lot of parameters in them. And you can always tell, in physics too, you can tell when I'm kind of scratching my head because I'm listing parameters. I'm using that to nudge my memory to get the right equation in my mind. So if it's got mass in it, you put down m equals. If it's time in it, you go t equals. If force in it, you go F equals, and you make a list. And you remember to put down what you've been asked. If you've been asked about acceleration, you put acceleration equals. And that will jog your memory. So you need to make a list. You need to write down the common symbol and unit of the unknown. Don't forget to put the unknown in. You look down your list of equations and you pick out the right equation. They're going to be in your head, but you pick out the right equation. Then you substitute in. So now we're finally at some numbers. We're on what? 5 of 7 steps. Now we put numbers in. We rearrange. And we get our answer. We say, does the answer make sense? The math bit is, in some respects, the least important bit. You've still got to get it right. We can't have math errors. But the physics is done in the first bit. Some people tend to over-focus on the numbers, and they'll just use the wrong expression, or they'll have the wrong prefix. They'll be using a prefix for it, etc., making a mistake like that. So I mean that from the heart. So let's